Let's look at paper 6.1, May-June 2019, alternative to practical. We'll consider all the 3 questions available in this particular paper. So, question 1, the diagram shows the apparatus a student used to prepare a dry sample of chlorine gas. Chlorine is more dense than air. So, question A says complete the boxes to name the apparatus. Complete the boxes to name the apparatus. And question B says use the diagram to identify 2 mistakes the student made. So in solving questions like this, 2 things are very important: ability to identify apparatus with their particular uses with respect to the kind of experiment that is being described, and the second is understanding the proper setup for a particular experiment. Okay, so in this setup, this particular apparatus here is a gas jar, and it's used for collecting gases produced in a particular experiment. And this particular one is a conical flask. It should be used to a conical flask. Now, the second question, talking about mistakes the student made. Okay, so studying this setup, if this setup is used to produce a gas, okay, and this particular conical flask, that is the last flask from which the gas will enter into this tube, okay, to go upward, needs to be covered. This conical flask is not covered, so that is error 1. And the second error here will be the inversion of this particular gas jar. The gas jar is used to collect chlorine, and in the question it was said that chlorine is more dense than air. So if chlorine is more dense than air, then it cannot be collected by upward delivery. Upward delivery simply means that the way this tube is arranged, you can see chlorine gas will go upward this way. So since chlorine is more dense than air, chlorine would then displace air. That means the chlorine will flow back down. So if chlorine flows downward, then it's going to escape into the atmosphere, into the surrounding. Then the chlorine gas will no longer be collected. That means the chlorine gas will be lost. So for gases that are more dense than air, you use downward delivery. For gases that are less dense than air, you use upward delivery. Okay, since they are less dense than air, that means they will stay in the gas jar. Okay, so now in response to B, so the first error we saw was that the second conical flask was not covered. The second conical flask was not covered with a rubber bung. Okay, the bung could also be called a cork. And the second error was that the gas jar was inverted. The gas jar shouldn't have been inverted. The gas jar was inverted. So that you are going to score your 2 marks. Get your 2 marks there, and you will be correct. Okay, so that's absolutely correct. You score 1 mark here, and of course you score the second mark there. So responding thoroughly to question is very important. Now, suggest 1 reason why the gas produced in flask 1 is passed through the concentrated acid. Okay, so let's look at the setup again. Now, the gas is passed through concentrated sulfuric acid. Well, the concentrated sulfuric acid has the ability to absorb water. Okay, so one of the uses of concentrated sulfuric acid is it is used as a dehydrating agent. A dehydrating hydrating agent. So the reason is to remove water, or if you like, say to dry the gas. That's the reason. Okay. Then describe a test for chlorine. Describe a test for chlorine. Now, if you look at this, you have 2 marks for this. To score your 2 marks, you need to describe first a test and the observation. It simply means that when the test is carried out, what are the likely things that will be observed? Okay, to test for chlorine gas, you use litmus paper. Okay, so if you use litmus paper, it could be, if you use blue litmus paper, okay, chlorine gas is slightly, acidic in nature. So what chlorine will do to the litmus paper is that it's going to, if it's blue litmus paper, you're going to turn it slightly red, then it bleaches the litmus paper. So the observation is that the litmus turns white, or you say that chlorine bleaches the litmus what? The litmus paper. Chlorine bleaches the litmus paper. So you score your 2 marks here, and of course your 1 mark here. That's how the marks are distributed. Very important that you know that. Okay. E, suggest why this experiment is done in a fume cupboard. So usually when experiments are done in a fume cupboard, it's basically because the gases produced will be a poisonous gases. So if poisonous gases are produced, then you have to perform the particular experiment in a fume cupboard so that the poisonous gas will not be released into the laboratory. So the reason is because the gas produced is poisonous. Gas produced is poisonous. It's as simple, as that. Okay, score your 1 mark. Now, let's look at question 2. This is where it gets, practical work gets interesting. Now, to answer your question 2 properly, you need to be careful in reading through the procedure stated. Take your time, work with time, but you have to take your time too to read the question carefully. Okay, a student investigated the reaction between aqueous sodium carbonate and aqueous barium nitrate. So you can see all the procedure here. A burette was filled with aqueous sodium carbonate. That's step 1 there. Then 7 test tubes were labeled. You have the first test tube 1, test tube 2, test tube 3, 4, 5, 6. They were labeled separately. Okay. Then a measuring cylinder was used to pour 6 cm cube of aqueous barium nitrate into each of the 7 test tube in a test tube rack. So now 1 cm cube of aqueous sodium carbonate was added from the burette into the test tube. So basically you have 7 test tubes containing sodium, 7 test tubes containing sodium carbonate, but the amount of sodium carbonate put into each of the test tubes differ. So the first test tube has 1 cm cube, second 2 cm cube, and it continues until you have the last test tube containing 8 cm cube of sodium carbonate. So if you look at this diagram of setup put there, these are the 6, the 7 test tube, the first, the second, the third. So you have different volume of sodium carbonate put into the test tube. Okay, now the next thing that was done was that a measuring cylinder was used to pour 6 cm cube of barium nitrate into each of the 7 test tubes. So the 7 test tube contain 6 cm cube each. So that tells us that this is like a constant. You should be able to identify your variables. It's important in an experiment: dependent variable, independent variable, and constant. So 6 cm cube here was constant all through. Now, a glass rod was used to stir the content of each of the tube. The content of the tubes were left to stand until the solid had formed or had settled. So a ruler was used to measure the height of the solid formed in the tube. So you have an instruction here: use a ruler to measure the height of the solid formed in each test tube shown in the diagram. Record the height of the solid formed in the table and complete the table. So basically what you have to do now, the reaction has taken place between sodium carbonate and what? And barium nitrate. So let me explain that. Basically, when these two salts react together, you have your barium nitrate, okay, barium nitrate plus sodium carbonate. The two of them are soluble salts. When they react together, you have something like a double displacement reaction, in which the sodium will displace the barium and it's going to form sodium nitrate. It's going to form sodium nitrate. Sorry, my formula was wrong. Sodium nitrate plus barium carbonate Barium carbonate is the insoluble salt here that forms the precipitate whose height you are trying to measure. Okay, that's basically the chemistry behind this particular experiment. So what you need to do now, you need to measure the height of the precipitates formed. The height of the precipitate, you can see this precipitate, you measure the height of the precipitate with a ruler. Okay, so I've got my ruler. I'm measuring the height of the precipitate with my ruler. Okay, but before we measure, let us fill the table because it's very important. The first here, the volume of aqueous sodium carbonate, you just need to pick it from here. We have 1, okay, 0.0. The next one, it's 2.0. The third one, that's 4.0. Then we have 5.0. Then we have 6.0. We have 7.0. And we have 8.0. That's the volume of sodium carbonate in cm cube added. So now I'm measuring the height using my ruler to measure the height here. Okay, the height of the precipitate form, I got 1.2 centimeter. 1.2 centimeter. So, but the unit has to be in millimeters. So you need to be very careful when you're solving your question. The unit is in millimeters. So I'm writing that. How do you convert centimeter to millimeter? 1.2 centimeter is equals to 12 millimeter. It's just conversion factor is times 10. Okay, so I have my 12 millimeter. The second one to measure with my ruler, that gives me 2.4 centimeter. That is 24 centimeter. I measure the next height with my ruler. I got 4.8. That is 48 millimeter. The next one measured with my ruler. Okay, I got 60 millimeter. Then next one measured with my ruler, I got 73 millimeter. The next one measured with my ruler, I got 73 millimeter. Then the last one measured with my ruler, okay, got 73 millimeter. So the tables have been filled there, and of course you're going to get 3 marks for filling your tables correctly. So very important to fill the table. All the tables filled, 3 marks, for filling the tables, correctly. So the next thing that we need to do now is to answer question B. So plot the results on the grid. Draw 2 intersecting lines of best fit label the x-axis. So maybe we should label the x-axis first. Okay, so let's label the x-axis. You have the height of solid in millimeter cube. So here, this is your x-axis. So what should our label be? That should be the volume of sodium carbonate, added in what? In centimeter cubed. Okay, volume of sodium carbonate added in centimeter cube. So let's plot the graph. So you're plotting the graph of volume of sodium carbonate in cm cube against height. Okay, against height. So you have for when 1 centimeter cube was added, 1 centimeter cube of sodium carbonate was added, we have the height is 12. So you go back to your graph. When 1 was added, okay, you have 12. Now look at the graph here. Each of the tiny boxes represent what? Okay, if you have 10 graduations here, 1 2 3 4 5 6 7 8 9 10, then each should represent 2 millimeter. Okay, 2 millimeter, and you have 12 millimeter. So this will be 10 and this will be what? 12 millimeter. So here, okay, that's the point. Then for the next one, which is 2 millimeter, 2 cm cube, you have 24 millimeter. 24 millimeter for 2, you have 24 millimeter. Okay, so 24 millimeter should be somewhere here. Okay, then the next one, your height here is what? 4 centimeter cube, 4 centimeter cube, 4 centimeter cube. So you have, for 4 centimeter cube, you have 48 millimeter height of the precipitate form. So this is where 40 is. Then 48 should be 1 2 2 3 4. This should be 48. Okay, 48. We had that 48. So the next one, height is 5. Let's just take it once together. 5 6 7 8. Okay, so we can just move on like that. 5 centimeter cube. 5 centimeter cube is 60. 5 centimeter cube is 60. So this is 60 at 5 centimeter cube. This is 60. 5 centimeter cube will give us 60. Then the next one is 6 centimeter cube, give us 73. Okay, this should be 62, 64, 66. This should be 70. This should be 72. Then in between here, it will be 73. Okay, 73. Then at 7 centimeter cube, we also have 73. Okay, at 8 centimeter cube too, we have 73. Okay, so now we need to draw the line of best fit. We need to draw the line of best fit. Now, in drawing the line of best fit, we have, it says draw 2 intersecting lines of best fit. 2 intersecting lines of best fit. Okay, so let's do that. Get your ruler. You need to draw accurate, lines of best fit now. Okay, so let's draw the line of best fit for this. So you need to be careful with that. Choose a line of best fit. Okay, let's go. Okay. Okay, something like that. Then second line, you're supposed to draw 2 lines that intersect. Good. That's 2 beautiful line of best fit. So, having drawn the line of best fit, let's try to answer the question that follows. From your graph, deduce the height of the solid form when 3 cm cube of aqueous sodium carbonate is added to 6 cm cube. So, at 3 cm cube, you are supposed to deduce the height. So, what we'll do basically is to extrapolate from this point, okay, do an extrapolation upward, okay, then you trace it back to this, trace it to get the height, okay. So that's should be 38, that should be 38 millimeter, 38 millimeter, okay, 38 millimeter. Good. Now, to score your 2 marks for this particular question, you need to show, don't just write 38 millimeter, okay, 38. Show from the graph and on the grid. Show from the graph and on the grid. So you're going to be scoring the 2 marks for that distribution. So the mark distribution, you're going to be scoring 1 mark for this, and of course you're going to be scoring 1 mark for showing it on the grid. Okay, so that's the mark distribution. The next question, describe the trend in the heights of the solid formed in test tube 1 to 7. Okay, so let's look at the height again. You can see that from test tube 1 to 7, the height increases, okay, then later levels out, and that is exactly what is shown on the graph. Okay, the graph actually tells us pictorially, diagrammatically, okay, at a glance, the way the height of the precipitate in the test tubes are vary. Okay, so how do you put your responses down? Simple. Okay, the heights of solid increases from tube 1 to tube 6 to tube 5, and then remain the same or becomes constant from tube 5 to tube 7. Okay, that's basically okay. So let's answer the next one. So what are the things that's responsible for the mark distribution here? Talking about the fact that the height increases, and of course it remains what? It remains constant. So the height increasing, okay, and of course it's remaining the same or remaining constant. Predict what will happen if the experiment were continued using 3 further test tubes containing 6 cm cube of aqueous barium nitrate. The barium nitrate has always been constant, and separately adding 9, 10 and 11 cm cube of aqueous sodium carbonate to each one, and you have to explain your answer. So this question is in 2 parts. You have predict what will happen and explain what will happen, or explain what you predicted. Okay, now let's go back to this. You can see that even when 8 cm cube, okay, of sodium carbonate was added, the level still remains the same. When 7 cm cube was added, the level remains the same. When 6 cm cube was added, the level remained what? The same. So usually in rate experiment when your graph goes like that and levels out. That tells you that at the point where it begins to level out, the reagents or either of the reagents has been used up. So addition of the other one will not make the reaction to continue or progress until the two reagents required for the reactions are available. The reaction will not progress. So applying that to this, predict what will happen. Okay, there will be no reaction, no further reaction, basically no further reaction. So what we'll have is that the height will remain the same. Remains what? The same. Remains the same. That is at 73 millimeter. It remains the same. And the reason is pretty simple. Okay, because this is because the barium nitrate, okay, the barium nitrate is used up. Okay, the barium nitrate is used up. It's as simple as that. Okay, so just one change to the apparatus used, which could be made to obtain more accurate result. Okay, to the apparatus used. So you need to go back to the experiment. In this particular experiment, what was used for measurement, apparatus for measurement? You use a burette. A burette is a fantastic apparatus for measurement of volume. Okay, you could have used a better apparatus. So we cannot find an improvement here. Now the use of a measuring cylinder to measure cm cube, okay, of barium nitrate into each of the 7 test tube. Okay, we could suggest a better apparatus that could be used. Instead of using a measuring cylinder, we could use a burette or a pipette. Okay, so using a burette is an improvement on this. Okay, so let's just choose a burette. Okay, a burette could be used instead of a measuring cylinder for barium nitrates. Yeah, for barium nitrates, you just need to be as specific as possible. Okay, so just a different method to measure the amount of solid formed during the experiment. So during this particular experiment, the amount of solid form was measured, and in terms of height, we use height to measure the amount of solid. It was measured in terms of the height of each of the solid form in the tube, talking about the height form. Okay, what else can we do? We can actually measure mass. We can measure the mass of the solid formed after the experiment. Okay, so how do you measure the mass? In this case, there's a little bit of problem. Measuring the mass of precipitates will be difficult because the precipitates, okay, are inside the liquid in the test tube. So the first thing that will be done is to filter off the precipitate. Okay, you have to filter. So you have to filter off the precipitate. Okay, after filtration, then you can dry the precipitate. That's the solid. In this case, it's the solid. Dry the precipitate and weigh. Okay, so you can weigh. Then of course you can record your mass, record the masses. Okay, so that's one way to do that. You can see 3 powerful steps there. Filter, you dry the precipitate, and of course you measure the mass of the precipitate. Then the last question here says, suggest how the reliability of the result could be checked. Basically, in your experiment, anytime they talk about reliability, what you need to do is just repetition. Repeat the procedure, collect results, and compare. So basically, you carry out the procedure again, then you collect the result and what, and compare. Okay, so basically here you repeat the procedure and compare the data. Repeat the procedure, compare the data or results. Fantastic. So when you do that, this is, you score your 1 mark for this. Just 1 mark for this, and for this, which is 3 marks, filtering, drying the sample, and of course finding the mass. You get your 3 marks correctly. Okay, and of course here you have using the burette. Okay, then for this particular question, the mark distribution, I'm just going through the mark distribution because it's very important. The height remains the same. You are expected to predict, okay, and explain. So you have predicted 1 mark, and of course the reason you gave 1 mark. Okay, so let's look at question 2 quickly. Question 2. Two substances F and solid G were analyzed. Solid F was dilute hydrochloric acid. Then tests were done on solid F and solid G. So test on solution F. Complete the expected observation. Solution F was divided into 4 equal portions in 4 test tubes. The pH of the first portion of the solution F was tested. So you're supposed to tell us the pH of this. Anytime they ask for pH, okay, they're actually asking for specific number, not whether the substances are acidic or basic. Okay, so when they say pH, give them numbers. Okay, so for this case, it's hydrochloric acid. Hydrochloric acid is a strong acid. So the pH of strong acid ranges from 1 to 3. So basically 1, 2, or 3 will be fine. Okay, so we just told you pH here is 1. Okay, now magnesium ribbon was added to the second portion of solution F. The gas produced was tested. Okay, so you are supposed to state your observation. You're supposed to state your observation. So here, 3 marks, very important for you to know how to put your responses down. Now you have magnesium with solution F. Don't forget that solution F is hydrochloric acid. So this is a reaction between magnesium plus hydrochloric acid. You're not supposed to write the equation. I'm just showing it so that you know the underlying chemistry behind this particular question. So you have magnesium chloride will be formed plus what? Plus hydrogen gas will be released. Okay, so hydrogen gas is released. So if a gas is released in a particular reaction, so what's the basic observation? You see bubbles form. Bubbles will be formed, or you describe that as the solution fizzling, or you describe it as what? As effervescence. Okay, so the observation for this will be effervescence. That means bubbles. Okay, so you can say bubbles are formed. That means effervescence, or you see fizzling. Okay, then what other thing can be seen? The gas burns. Okay, with a squeaky pop sound. Okay, so you have 3 observations here. The gas burning, and of course it makes a squeaky pop sound or pop sound. Then the presence of effervescence. So that will earn you your 3 marks for that. So you have 3 marks. Your pH, that's a mark, and of course the fact that you have bubbles will get a mark. Okay, and of course the presence of a flame burning, indicating burning, and of course for the pop sound you get 1 mark. Okay, so let's move on to the next question there. Okay, dilute nitric acid and aqueous silver nitrate was added whenever you have silver nitrate, with something that contains a chloride, don't forget that solution F contains a chloride. So you have a reaction there that will be formed between silver and of course and the chloride, because solution F is hydrochloric acid. Of course you would expect that in hydrochloric acid you have a chloride. So silver plus chloride there will definitely give you a white precipitate of silver chloride. So your observation is you have the white precipitate. The white precipitate is formed. White precipitate is formed. That's your observation. Dilute nitric acid and barium nitrate were added to the 4th portion of the solution. So you have barium nitrate being added to the chloride, which is hydrochloric acid, and of course in the presence of nitric acid, certainly there will be no reaction. No reaction will be observed here. No reaction basically will be observed. So let's move on to the next question. And that is test on solid G. Test on solid G. So basically this part of the questions, you have the observations were already written. They say some of the tests and observations are shown. The appearance of solid G was studied, and it was shown that solid G is a white solid. Then they carry out 2 tests on solid G. Dilute hydrochloric acid was added to solid G. The gas produced was tested, and you have rapid effervescence. The gas was tested and it was found out that the gas turned lime water milky. That's a common suspect there, right? You're suspecting a gas to do that. What gas does that? It's carbon dioxide. Carbon dioxide, when it bubbles into lime water, lime water is calcium hydroxide. So when it comes, carbon dioxide enters into lime water, definitely it produces calcium carbonate, which gives you the white precipitate that you see, that makes the lime water become milky. So the test 2 says the solution formed was then divided into 2 portions. That is, the solution formed here divided into 2 portions. Now excess of sodium hydroxide was added to the first portion of solution from the test, while precipitate formed, which was insoluble in excess. Then you have an excess of ammonia was added to the second portion of the solution from test, and there was no precipitate. So let's look at the question. So it says identify solid G. Identify solid G. So if you look at your qualitative analysis test, you will find out in your qualitative analysis test that the suspect here is calcium. Calcium forms white precipitate in drop-wise sodium hydroxide, but the white precipitate remains insoluble in excess. Remains insoluble in excess. So you're suspecting calcium there. Then of course, in reacting with ammonia, ammonia was added to the second portion, and we have no precipitate formed. So for us to conclude, let's look at the qualitative analysis page. the qualitative analysis page, okay, you should be familiar with this. This is talking about tests for qualitative analysis, tests for anions, and of course tests for cation. So if you check through, we have a substance that forms, white precipitate with few drops of sodium hydroxide, white precipitate with few drops of sodium hydroxide, okay, with few drops of sodium hydroxide, okay, and it's insoluble in excess, okay. Then when it is reacted, it was reacted with aqueous ammonia, you have no precipitate or form. That means no reaction, no visible reaction form. So you can see here that calcium is implicated as the cation present here. Then talking about carbon dioxide being produced, okay, carbon dioxide being produced when you have dilute acid, okay, added to a substance that contains a carbonate, you have effervescence and carbon dioxide produced. So if carbon dioxide is produced, how are we sure that carbon dioxide was produced? Let's go and see for the test for carbon dioxide. Carbon dioxide turns lime water what? Milky. So when you put all these pieces together, then we'll arrive at answer that calcium was present, calcium ion was present, and of course carbon dioxide was formed from what? From carbonate. So we can conclude that solid G is calcium carbonate. Very simple conclusion, very simple conclusion. So the mark distribution for this, you have 1 mark for calcium and 1 mark for what? For carbonate. That's the mark distribution for that. And of course these ones are just 1 mark each, okay, 1 mark each. Now let's move on to the last question. I hope it's been interesting, right? Okay, now for this last question, it's basically about planning experiment. So to plan your experiment, you need to read the question thoroughly and try to give it a topical sense. I like to say that. Give it a topical sense and try to just picture in your mind what kind of experiment are you talking about, what kind of setup will be required, what kind of apparatus will I need to use, what quantity will I need to measure, what will be my dependent, my independent, and my constant. So you need to have a thorough understanding of of your variables, okay, and of course the apparatus that is needed to measure a particular variable. So the most important thing to note here when planning experiment, okay, apparatus to use, okay, apparatus to use, what measurement to take, okay, what measurement to take, okay, what do you need to vary, okay. So you need your variables, very important. You need to identify your variables, okay, and of course how you need just 1 sentence to serve as a simple conclusion, okay. Now so let's look at this question together. It says steel nails rust in the presence of air and water. Plan an investigation tool. In fact, you've been told what your investigation will what the result will look like of your investigation and what your conclusion is all about, okay. Here you have show that coating steel nails with paint helps to prevent nails from rusting. The same thing that when a steel nail is coated with zinc, it helps to prevent it from rusting, and of course determine which coating is more effective. So there are 2 things you are finding out here. You are finding 1, which of these 2 methods of preventing rusting is the best. That is painting and with painting and of course galvanizing. That's use painting with zinc if you like, okay, or coating with zinc, coating with zinc, okay. Then you want to determine which is the best, and of course you also want to show that each of these actually protect the nails from what? From rusting, okay. So a typical planning will look like this, okay. Let me just try to be very expressive for you, okay. So what you do first here, okay, if I was to plan this experiment, I will weigh, okay. So we'll weigh the nails. I'll weigh the nails and record their initial mass. I will weigh and record their initial mass. Okay, then the next thing is I'll place each nail. I'll place each nail in a boiling tube with good, in the boiling tube. Okay, just a suitable container in a boiling tube, and then I'll add water. Then I'll add water, okay, to the nail. Okay, water is required for roasting, and of course air, okay, will be there. The boiling tube will be left open. Okay, the boiling tube tubes will be left opened. Okay, then the next thing will be I'll allow time. I'll let the setup stand for, okay, let the setup stand for, say, for about 2 weeks. Yeah, anything more than a week is fine. For about 2 weeks. Then I'll remove and reweigh. The nails. Okay, then when that is done, the next thing will be to compare the masses. Compare the new mass or masses with the initial. It's just very simple, with the initial. Okay, so you need, when you have done your comparison, you need a statement to conclude. Now that's very key. Statement of conclusion is very key. Okay, so what would the statement of conclusion look like here? The nail with lesser mass increase, because we are looking at if there is an increase in mass. The nail with the lesser mass increase has best coating. That's very, very simple indeed. Has best coating. So the marks attached to this question is six marks. Okay, so let me show you a possible mark distribution. So a possible mass distribution. We talk about weighing, okay, the nails. Okay, weighing the nails. That's one. Then of course placing the nail in a suitable container. Okay, that's another mark. Okay, yeah, talking about letting the setup stand for a week or two. That talks about the time frame for the experiment. Okay, yeah, removing and reweighing. Yeah, that's another mark. Comparing, that's another mark. Okay, and of course your conclusion. Okay, that gives you your 6 marks. When you have all this in mind as you plan an experiment, okay, just follow the procedure, identifying your variables, identifying the apparatus, identifying the measurements you need to make, and of course write your statement sequentially. Then always conclude well. Always conclude well. Okay, thank you for being with me in this online class. I'll catch you in my next video. Remember to subscribe to my YouTube channel, and you can visit www.eridonlineacademy.weebly.com for more resources and for more video. Always believe in yourself. You can do it. Yes, you can.